Hi class, today we're going to talk about liquids and solids. The last chapter we dealt with gases and gas laws and did some calculations with that. This chapter we're mostly going to focus on liquids and a little bit on solids, but mostly liquids and some special concerns that we have when we're dealing with liquids. So let's talk about what's going on when things are in the liquid and solid state. This quiz, why don't you try and answer this quiz. You can pause the recording and see what you think the answer is. All right, the answer to this question is really the focus of this whole chapter. And the answer as to what the attractions between molecules are called cohesive forces. And we're going to learn about the three main types of cohesive forces and how they affect things like vapor pressure and boiling point and melting point. So that's really the main idea in this chapter of these cohesive forces. So liquids and solids are held together by cohesive forces. They're the attractions between atoms and molecules when they get close enough that they can interact. In gas phase molecules and atoms, there are no interactions. That's one of the reasons the gas laws that we learned about work, is because there is no attraction between the molecules. They're far enough apart. They don't interact. They don't veer out of the way when they're traveling in a straight line. But in liquids and solids, essentially the atoms and molecules are touching. And they're touching because of these cohesive forces. A good example of cohesive forces in action is what would happen to a liquid droplet. If you were in space and you had a little droplet of water free to float around, it would take the shape of a sphere because of these cohesive forces. A sphere is the lowest surface area to volume ratio, and it allows these cohesive forces to maximize. Here's a couple links. You can actually watch these. I won't show these, but you can copy and paste these if you want to see what these things look like in space, what gravity or lack of gravity does to these liquids as far as the cohesive forces go. So this picture shows the three main states of matter. We're not going to talk about Bose-Einstein condensate or plasma. These are the main forces or main types of matter that we encounter in normal life. And the main difference between these is just the distance between the molecules. The gas phase is on the left-hand side. The molecules are far apart. There are no cohesive forces. In the middle, the liquid molecules are actually touching each other. There are attractions between those molecules. And there's still a lot of movement. They can bump into each other and roll around each other, but they're still free to pretty much move as they want. In the solid phase on the right, the atoms or molecules are held in a fixed position. There still is movement in this fixed position. The molecules are vibrating in that fixed position, but they can't move out of that fixed position. They're held. That's what makes a solid keep its shape, whereas a liquid just kind of goes wherever it wants to go when it's poured out of a container. We're going to talk about some of the phase changes that liquids undergo when they turn into gas, and those are the most interesting. Evaporation is one of the phase changes that a liquid can undergo. If you look at this beaker, all of these molecules or atoms are touching each other. They're being held together by cohesive forces. They do have kinetic energy and they're moving around. The ones on the surface don't have an equal amount of attraction above and below them. There's nothing above them that's attracting them, and there's a whole bunch below. And so actually it turns out to have like a little film. It's kind of some unequal forces on the surface that's called surface tension. But every once in a while, one of these atoms or molecules on the surface gets enough energy to overcome these cohesive forces, keeping it as a liquid and escape into the gas phase where there are no more cohesive forces. So this is, evaporation is a surface phenomenon only. And you should remember that. Evaporation is a surface phenomenon. Just atoms and molecules on the very top layer can get enough energy, enough kinetic energy to escape into the gas phase. And it's because there are fewer neighbors and less interaction and unequal force. So as long as they can get enough energy, they can escape. So really, these cohesive forces, the battle is between cohesive forces and the kinetic energy that the substance has. Kinetic energy is the energy of movement. And if you have enough kinetic energy, you can overcome the forces that are keeping you in a liquid phase. So vapor pressure, the definition of vapor pressure is the pressure of the gas coming off the liquid. So this gas is going to have a pressure because it's in the gas phase, and it'll have a pressure. The more gas phase molecules here, just as we learned with the gas laws, the higher the pressure. Vapor pressure is a really good sign as to how much of a cohesive force the liquid has. If there is a very high vapor pressure over a liquid, it means that the molecules that are in the liquid can very easily escape into the gas phase. So high vapor pressure equals low cohesive forces. And you should remember that. High vapor pressure equal lower cohesive forces. A low vapor pressure means that the molecules in the liquid really like to be attracted to each other, and it takes a lot of energy to escape into the gas phase. So low vapor pressure equals higher cohesive forces. All liquids have different cohesive forces. That should be different, not difference. Different cohesive forces, which means it's a different amount of energy required to escape into the gas phase. And this is what I just said. Now you have it written down. High cohesive forces means a low vapor pressure. And a high vapor pressure is just the opposite. So water, a sample of liquid water has pretty dang high cohesive forces. And it means the vapor pressure of water is quite low relative to something like gasoline that doesn't have very much cohesive forces, and it can escape into the gas phase quite easily and quite readily, and it has a high vapor pressure. If you had a container of gasoline and a container of water, the gasoline would much more easily evaporate and more quickly evaporate in the gas phase than the water would. If the containers and the amounts of the two liquids were the same, and that means the gasoline has less cohesive forces, keeping it as a liquid. So what happens when a liquid evaporates? What happens to the temperature of the liquid from which the stuff is evaporating? Pause the video and see if you can answer this question, and then we'll proceed. The answer is the temperature of the liquid decreases as the evaporation process happens. The reason this happens makes sense is because the higher energy molecules are escaping into the gas phase, which means on average the kinetic energy of the sample, the liquid sample, is decreasing as the evaporation happens. This is how evaporative cooling works. Our bodies are cooled by evaporative cooling. We sweat, and as the sweat evaporates, the higher energy molecules are removed into the gas phase, and it leaves behind lower energy liquid, lower temperature liquid, and so our body is cooled. That's evaporative cooling. Swamp coolers are the same thing. They take the high energy hot air molecules, and that's used to evaporate the water, leaving the water that's left behind cooler. And so, this is a really important process. When you go swimming, you jump in the water and you're covered with all the water, and you hop out of the pool and the water starts evaporating. Well, gosh, after a few minutes, you jump back in the pool, and I, as a kid, I was like, man, the water is so warm and nice when I jump back in the pool. And the reason is because it is much warmer than the water that's left on your body after you've been standing out for a while, because of that evaporative cooling that goes on with the water that stays on your body, and some of it is evaporated. Then you jump in and the temperature is several degrees warmer than it was before the evaporative cooling happened. Another quiz. So pause the video and see if you can answer this quiz, and we'll continue. So number 4 is the right answer. If you have a very volatile liquid that escapes easily into the gas phase, the temperature of the remaining liquid decreases. You may have noticed, like when you get a shot in your arm, and they put some alcohol on a cotton ball and rub your arm to kind of as an antiseptic, that the alcohol evaporates very quickly because it has lower cohesive forces than water, and it feels cold, doesn't it? So the temperature decreases as something is very volatile. The temperature of the remaining liquid decreases. So solids, we're not going to spend a lot of time on solids because they're really not as interesting as liquids, but essentially a solid is a well-ordered structure where all the atoms are held in a fixed position. There is still movement. This picture on this slide is essentially water held in the molecules of water are held in fixed position. So this would be the solid phase of water, or we'd call it ice. The molecules in ice are still moving, but they're not moving as much as in liquid. They are vibrating in that fixed position. You can actually make ice colder than the freezing point of water. If you keep cooling the ice down, it can get absolute zero is the point where there is no more vibrational movement. So that's the Kelvin scale, is when the atoms and molecules stop all vibrational movement and they stay in one position. That is absolute zero. So the solids, what keeps them in the solid state is because the cohesive forces are so much more dominant than are the kinetic energy. There is not any kinetic energy essentially to move them out of that fixed position. And so the atoms stay where they're at, they interact more, the cohesive forces are by far the dominant force in a sample that's solid. In a liquid, kinetic energy is there, but there's also cohesive forces. In a gas phase, it's all kinetic energy. There are no more cohesive forces between the molecules. So remember, we're talking, these forces are between the molecules. They're not, up until now, we've always talked about like bonds in a molecule. This is interaction between molecules. So answer this question and pause the video, and then we'll go on. The answer is actually false. When you boil water, you are not breaking any covalent bonds. All you're doing when you're boiling water is allowing the water to overcome the cohesive forces and escape into the gas phase. You may ask, well heck, what's the difference between boiling and evaporation? Because evaporation, we just talked about a few minutes ago, is also that escape into the gas phase. But boiling is a special kind of magical point that we'll talk about what boiling is. But there are no bonds broken. You're not breaking the hydrogen-oxygen bond when you boil water. You're just overcoming all cohesive forces, and then the gas phase water has now just got kinetic energy. So again, these kinetic energy versus cohesive forces, these are the competing forces in liquids and solids. In solids, cohesive forces win. In liquids, there's a battle between those. In gas phase, the kinetic energy has won. And which one dominates determines which phase the substance will be in at a given temperature. Whether it's, if the cohesive forces are stronger than the kinetic energy, if there's still enough kinetic energy, it'll be liquid. If the kinetic energy is too low, then the substance will be in a solid phase. So the melting point of a substance is the point at where there's enough energy to overcome the cohesive forces and at least get the things moving, rolling over each other, bumping into each other. They're not held in a fixed position anymore. So every pure substance has its own unique melting point. And that's actually one way to tell if something is pure, is by doing a melting point determination. If you know, you've tried to create a substance and you know what the melting point should be, if it is different than what the pure substance should be, then you don't have a pure substance. So this is a very powerful, easy tool to test the purity of drugs or whatever. Drug companies use melting point determination all the time. So that is a very defined point, and every substance will have its own unique melting point where the cohesive forces are started to be overcome by kinetic energy. The boiling point is this magical point where the kinetic energy is completely overcomes the cohesive forces and the molecules can escape into the gas phase. And one important thing why boiling is different than evaporation is at the boiling point, the vapor pressure of the liquid that's boiling is equal to the pressure of the atmosphere pushing down on that liquid. That is the magical point of boiling, where the vapor pressure is equal to the atmospheric pressure. And I might pause now and draw a picture of that, depending on what the next slide says. But let's talk about this slide. Then I'll pause for a minute and work on the board. So again, are you breaking chemical bonds when you melt or boil something? No, you're not. You're just overcoming cohesive forces. If you actually wanted to separate the oxygen and hydrogen in a water molecule, it would require much higher temperatures, or you'd have to use a different technique to do that. But you're not breaking bonds, you're just overcoming the cohesive forces. And the strength of the cohesive forces are related to the molecule structure and, are related to the molecule structure. And so a lot of this chapter we're going to learn about the three types of cohesive forces that molecules can have and how it affects things like vapor pressure and boiling point. And by knowing the molecular structure, we can determine how these cohesive forces are actually affecting things. So let me turn on the lights, and I want to just show you what I mean by vapor pressure equaling atmospheric pressure and boiling. Okay, so let's say we have a pan, and we put this pan on the stove, and we start heating it up. We've got water in here. As the water heats up, the kinetic energy is increasing of these gas molecules, or of the liquid molecules that are in here. We know that we do have some water, even if we don't have any heat under there, we still have some water that's evaporating. And the vapor pressure isn't very high because it's just at room temperature. But there is still some evaporative thing happening at the surface. As you heat up this, more and more of these have enough energy to escape into the gas phase. So the vapor pressure increases. So as the temperature increases, as T goes up, vapor pressure also goes up. As temperature increases, vapor pressure goes up. We have one other force that's happening on this, and that is the force of the atmospheric pressure. We know we have pressure from the air, the atmosphere, pushing down on this. And that pressure actually is a force that will try to keep things in the liquid phase as well. Well, if I draw a little arrow of the vapor pressure, when the vapor pressure is less than the atmospheric pressure, then it's just a surface phenomenon. It's just evaporating. But as the vapor pressure increases, it's gonna sometime exactly match the pressure of the atmospheric pressure. And so when the vapor pressure is equal to the pressure of the atmosphere, then there is boiling. And I think I've got some slides later that will also talk about that, but we'll do it here and then we'll review it again in a little bit. So what happens when something is boiling? No longer is it a surface phenomenon, but the bubbles are actually forming down on the bottom of the container, because that's where the most energy is putting in. They're able to get into the gas phase not on the surface, but in the body of the liquid. And the bubbles come up, and then it just escapes, and the vapor pressure is equal to the atmospheric pressure of that. So boiling doesn't happen at the surface; it happens throughout the liquid, and usually you just see the bubbles form here on the bottom, because that's where the energy is being inputted. They have enough kinetic energy right there to escape into the gas phase. So that's what's happening in boiling, how the cohesive forces are being overcome by temperature increase, making the kinetic energy be enough that that molecules can escape into the gas phase. But it has to be this, vapor pressure has to equal the atmospheric pressure in order for boiling to happen. Okay, so read this slide and see if you can answer this quiz question, and then I'll talk about the answer. So as long as there is liquid present in a substance that is boiling, the liquid is staying at the same temperature. The liquid has a maximum temperature that it can reach. And then all of that energy that goes in is added to just convert right into the gas phase. So the temperature of a liquid that's boiling stays constant. The gas molecules, they can be heated up further. If you were able to heat the gas once it was in the gas phase, you can heat steam as hot as you possibly can. That's why steam burns are way worse than liquid burns, because the temperature of steam can be much, much hotter than just the liquid from which the steam comes from. Okay, pause the video and answer this question. This is what I mentioned on the board when I did that. The vapor pressure has to equal the external atmospheric pressure, and when those things happen, that's when boiling occurs. Before that happens, it's just evaporation. The vapor pressure is increasing, but it's just evaporation, although the evaporation is happening more quickly because the vapor pressure is increasing. But it's only when the vapor pressure is equal to atmospheric pressure that boiling actually occurs. And just as a side note, you may have had pressure cookers, or your mom, all moms have pressure cookers. Some of you, you don't get a pressure cooker until you're older. I think it's one of the requirements to have a pressure cooker. Anyway, how that works is the pressure of the steam is actually kind of trapped. Well, not kind of, it is trapped inside this sealed container. It does have an escape valve. They're very safe, but the steam isn't allowed to escape. Therefore, because of, if you increase the amount of a gas in a constant volume, then the pressure is going to increase. Well, as the pressure increases, the boiling point of that liquid also increases. And so pressure cookers actually allow water to get hotter than it would normally be able to get at just in a pot that's boiling. You can get water that can get well over 212 degrees by using a pressure cooker. And what that does, it typically helps the food cook faster, and it can make meat that's otherwise very tough. It can tenderize it because you're really getting the temperature hotter that can make the meat tender. If you were to boil water at Mount Everest, for example, where the atmospheric pressure is way lower than it is at sea level, I think we calculated it was 0.3 atmospheres on Mount Everest. Well, what does that mean about the boiling point? Well, because the atmospheric pressure is so low, water will boil at a much lower temperature. It doesn't take as much kinetic energy to get the vapor pressure to the point where the atmospheric pressure and the vapor pressure is equal. So you can actually boil water, and it'll be boiling, and it might feel warm to the touch, but it won't burn you because it'll be a much lower temperature. All right, let's talk about the three types of cohesive forces. And you need to know these. You need to know how they affect things and what they are and how we identify them. The first one, which is the weakest that we'll talk about, is called dispersion forces. Sometimes in biology you call them van der Waals or London forces. Some of you in biology will know that terminology. These are the weakest forces, and we'll talk about what these forces are in just a minute. The next one is dipole-dipole interaction. This is the second strongest interaction between molecules. And the third one is hydrogen bonding, and by far hydrogen bonding is the strongest intermolecular attraction. Now that word I just said, I haven't said that before, but intermolecular means interaction between molecules. So these are forces, these are things that happen between molecules. If these cohesive forces weren't present, then everything would be in the gas phase because there would be no cohesive forces. There'd just be kinetic energy and everything would be in the gas phase, which, that isn't really good. We need things in solid and liquid phase as well. So let's talk about dispersion forces. This picture looks like some blue eggs, but they're really representing atoms or molecules, whatever, just some sort of entity. And we know that everything has electrons. So just in the random movement of electrons as they travel in the orbitals in the atom, there may be an instantaneous moment where there are more electrons near each other and less electrons in another part of the atom or molecule. And so these little pluses or minus means that just in an instantaneous flash of random movement, the electrons bunched up right here and made this part of the molecule partially negative. And that means there's a deficit here and this is partially positive. Well, when this happens with the atom next to it or the molecule next to it, the electrons in this one will go, oh baby, that looks kind of positive there. So the electrons will kind of come down here and there'll be a little attraction between these, a positive and negative attraction. And it just kind of spreads through a sample. And this is an instantaneous thing that happens to everything. Everything that has electrons will have this happen. It is the weakest force. It's present in everything, and you need to remember that. Dispersion forces, anything that has electrons can have this temporary bunching or uneven electron distribution in the atom or molecule. So it's present in everything. So this graph is something that is good to talk about because it tells about how these cohesive forces affect things. And how we know there's an effect is by looking at the boiling point. If you remember, boiling point is a really good indication of how much cohesive forces are present. If something has a high boiling point, it means it takes a lot of energy to overcome cohesive forces. If something has a lower boiling point, it means there's lesser cohesive forces. You should write that down in your notes because that's how boiling point affects how we gauge these cohesive forces' effectiveness. One way is the boiling point, another way is the vapor pressure. So these are the noble gases, and remember, noble gases, they're non-polar atoms. The only thing that they have going on is just electrons that are happy as clams orbiting around in filled orbitals. Well, even though these electrons are happy as clams in filled orbitals, there still might be this temporary bunching of electrons in a helium atom or in a neon atom or in an argon atom. The middle column shows the molar mass. And essentially we know molar mass is the sum of all the protons and neutrons, and we put it in units of grams per mole. Molar mass is also an indication of how many electrons are there. I mean, it doesn't say that there's 4 electrons. I mean, but the bigger the molar mass, it means there's more electrons in the molecule or atom. So if we look at the molar mass, it's increasing as we go down the column of noble gases. Helium 4 grams per mole, xenon 131.3. And you can look on a periodic table, and I don't have this memorized, but you can look to see how many electrons each one of these atoms has, and you'll see that it does follow that trend of smaller molar mass, fewer total electrons, and bigger molar mass, more electrons. If you look at the last column, the boiling point in unit of Kelvin, look at the boiling point of these things, from helium to xenon. So what this means is that helium really doesn't have very much cohesive force. It only has 2 electrons, and those 2 electrons, it's not a very strong force if they bunch together and try to be attracted to another helium atom. So it's pretty easy for helium to be into the gas phase. I mean, 4 Kelvin is really a cold temperature. It's almost absolute zero. But you can see that the boiling point increases as you get more and more electrons. And that is exactly the trend we'd expect, because we know the only thing that's happening between molecules, or not molecules, between atoms in samples of helium or neon or argon or krypton, the only thing that's happening between them are these dispersion forces. So bottom line is that the more electrons, the bigger effect the dispersion force will have on the boiling point. Now, vapor pressure, what would be the vapor pressure? Well, less cohesive force means higher vapor pressure. So you'd expect the vapor pressure to have the opposite trend of the boiling point, that things with less cohesive forces will have higher vapor pressure. And I don't have the data to show that for noble gases, but it's the same type of thinking. Okay, so pause the video and do this quiz, and then we'll talk about the answer. All right, the answer is higher. Hopefully you got that. A sample of molecules with stronger cohesive forces will have a higher boiling point than a sample of molecules with weaker cohesive forces. That's kind of the summary of what we've been talking about. And if dispersion is the only thing present, then it's the species with fewer electrons or smaller molar mass is going to have a lower boiling point than something that has more electrons, or a stronger cohesive force. Here's another slide, table 2 in your textbook. The alkanes listed are simple hydrocarbons, and they're pentane, hexane, heptane, octane. Pent means 5 carbon atoms with the maximum number of hydrogen around them. So, and hex means 6, and hept means 7 carbons. Oct means 8 carbons with the maximum amount of hydrogens, or saturated, we'd call that. So essentially we're adding 1 more carbon and more hydrogens as we go down that table. And so we're increasing in molar mass and number of electrons. And look what the boiling point is between heptane or pentane to octane. The boiling point does increase as you increase the molar mass, because octane, having the highest boiling point, has the most cohesive forces present, and the only cohesive force present in it is dispersion force. When you have a when you have a nonpolar molecule, like all of these are nonpolar, that's going to be the only force between molecules will be dispersion, or London forces. So there's a couple examples in your textbook you can do. I won't take time to do that here, but you can do the your turn and look at the answer and hopefully understand that. So the second cohesive force, the second most abundant, is called the dipole force, or dipole-dipole interaction. So dipole-dipole interaction between molecules are present in molecules that have permanent dipoles. You remember we learned about how to figure out if a molecule is polar or not? Well, we're going to apply that again in this setting to see, how it affects the interaction between molecules in a sample. So here's a picture of hydrogen chloride. It is a polar molecule. The chlorine is more electronegative than the hydrogen. And that's a permanent condition. It's not one of those temporary fleeting things like the dispersion force was, but it's permanent. And so the molecules will align themselves where they can be, they're like tiny magnets. The negative end of one will align with the positive end of the other one, and they'll maximize their attraction. That's a much stronger force than just a temporary induced dipole like we had in the dispersion forces. But you got to remember, just because something has a polar covalent bond, the whole molecule might be nonpolar. Remember that symmetry stuff. So you got to remember that stuff from that chapter. So here's a picture of 2 hydrogen chlorine molecules, and they'd be aligning the positive end of this hydrogen attracted to the negative end of that chlorine, and that's a pretty strong permanent attraction. That's how do magnets, there's pretty good attraction between 2 magnets, and that would be an example of an intermolecular force. It's just the same kind of force that magnets would have between them. So here you can see 2 molecules, ethane on the left and formaldehyde on the right. The molar mass of each of them are identical, but look at the boiling point. Ethane is a minus 88 degrees C, and formaldehyde is a minus 19 degrees C. So formaldehyde has a much higher boiling point. Now, are there dispersion forces present in a sample of ethane and formaldehyde? Well, the answer is yes, because everything has dispersion forces in it. What other forces are present that could account for such a big difference in boiling point? Well, ethane is a nonpolar molecule, so the only forces present in a sample of ethane between the ethane molecules would be dispersion forces. But formaldehyde, if you look at the Lewis structure, you should easily see that formaldehyde is a polar molecule. It's a permanently polar molecule. So a sample of formaldehyde would have dispersion forces, but would also have dipole-dipole interaction, which is a stronger force, and it would make it harder for formaldehyde to get into the gas phase. And that means the boiling point is going to be higher than that of ethane. So what I want you to be able to do, if I give you a list of compounds, be able to predict what the boiling point would be relative to each other. Which ones would have the highest boiling point or lowest boiling point based on your understanding of these dispersion forces. So that top statement is kind of the summary of all this. If a molecule is polar, then boiling and melting points will be higher than nonpolar molecules of similar mass. And that's a great example, the ethane versus formaldehyde. So as a review, do this quiz, pause the video and answer it, and then I'll talk about it. So the second strongest force is the dipole-dipole interaction, or dipole forces. And just a little diversion to talk about polarity and solubility and miscibility of things. So a polar substance won't mix with anything that is nonpolar. And I think I talked a little bit about this. I can't remember if I did or not. Like dissolves like, but here's a picture of maybe oil and vinegar or something. On the top layer, you can see these are nonpolar molecules, big old hydrogen-carbon chains, and in the bottom is some sort of it looks like water, but it looks like there's other things other than the water in there. But water, these are polar, these are nonpolar. These two things do not want to mix together. And the reason is because the molecules of this hydrocarbon, the only thing going on between those are dispersion forces. They don't want to be by anything that's polar. Because a polar molecule wants to be with something that has a negative and positive end, and a nonpolar molecule just doesn't. So they'll hang out with other things that are nonpolar. They will not mix with things that are polar. And the water is the same way. They don't want to be hanging out with things that don't have a positive, negative end. So the water will be with other water molecules or other polar molecules mixed in, and the oil will not. Soap is an interesting molecule because it's a bridge between polar and nonpolar. Essentially, a soap molecule. If you Google micelle, a soap micelle, M-I-C-E-L-L-E, M-I-C-E-L-L-E, it'll show a picture of how soap works. Essentially, a soap molecule it's got a big old nonpolar hydrocarbon end and an ionic salt end, essentially. I'm trying to remember the name of one of the soaps. Sodium lauryl sulfate, something like that, where it kind of tells you there it's got some ionic, but then it's got some sort of organic thing called laurel in it. Anyway, so it has a big old nonpolar end that can kind of encompass little oil droplets, and the ionic end can be in water, and so little oil micelles are formed, and the water can whisk these soap micelles away. So if you don't wash your hands with soap, you're really not cleaning your hands, because that's the only way to get oil and grease off of your hands is if you use soap. Just washing with water is really not effective. So anyway, here's Mama Caka. Make sure you wash your hands with soap. And actually they say to sing the alphabet song and run your hands under the water long enough to sing the alphabet song, and then you'll be in good shape and you won't get sick so much for not washing your hands long enough or in depth enough. The third cohesive force is called hydrogen bonding. It's a strong cohesive attraction between special polar molecules. So hydrogen bonding is only going to be present in some polar molecules. And here are the ones that can have hydrogen bonding. If there is somewhere in the molecule a hydrogen-nitrogen bond, a hydrogen-oxygen bond, and hydrogen-fluorine. This one isn't really that important because that's all that would be. It wouldn't have any other, because fluorine only wants like one bond. So these are the main two things we look for in a molecule that could, if it has hydrogen bonding or not. This has to be present. This hydrogen bonding is an incredibly important physical phenomenon of matter. The hydrogen bonding that's present in water, if you think about a water molecule, it's H2O. It has two HO bonds, doesn't it? And so it has hydrogen bonding between water molecules. And this leads to a much higher melting and boiling point than you would expect if the only thing that was there was dispersion and dipole-dipole. The boiling point, you'd think it'd be a little bit higher, but when you get hydrogen bonding present, the boiling point increases dramatically because it's such a strong cohesive force. It's very difficult, much more difficult to get something in the gas phase if there's hydrogen bonding present. I mean, it happens all the time. It's not impossible, but it takes more energy to do that. So the biggest examples would be water, ammonia, hydrogen fluorine gas. That's a bad example because it's actually, it's not interesting. But water and ammonia are, and any time ammonia is an example, it has a HN bond. It's NH3, so it's got 3 of those bonds. Another really important substance that has hydrogen bonding is the DNA strands. If you look at the molecular structure of DNA, what keeps those two strands together are nitrogen-hydrogen bonds on the two strands that keep those DNA strands together. So that's kind of an important hydrogen bonding example. A sample of alcohol, and alcohol will have, like methanol, is CH3OH. It has that OH bond, and so alcohol, it's a polar molecule, but also it has hydrogen bonding present. So here is an example of 3 substances, and they have about the same molar mass. So what this means is that if things have about the same molar mass, then the amount of dispersion forces are going to be about the same, because molar mass is a direct relationship to a number of electrons. So ethane is a nonpolar molecule. The only thing that a sample of ethane would have in as far as intermolecular forces go would be dispersion. Hydrogen sulfide, if you do the Lewis structure, you'll see it's shaped like water. It's a bent-shaped molecule, and because of the difference in electronegativity and the asymmetry, the hydrogen sulfide is actually a polar molecule. Methanol, here's that CH3OH that I mentioned. It is a polar molecule, but it also has an OH bond in it, and so there's going to be hydrogen bonding between the methanol molecules. So all 3 of these things will have dispersion forces. That's the only thing present in ethane. These 2, hydrogen sulfide and methanol, will have dipole-dipole interaction, and methanol is the only one that will have hydrogen bonding. And we know hydrogen bonding is by far the most powerful intermolecular or strongest intermolecular or cohesive force. And look at the boiling point. It's almost over 100 degrees higher because there is hydrogen bonding in a sample of methanol, whereas hydrogen sulfide, all it has going on is dispersion and dipole-dipole interaction. So it can much more easily go into the gas phase than methanol. So here's a couple molecules. It looks like we've got a couple lone pairs missing on this oxygen, and a couple lone pairs missing on this. There's just And we need 2 lone pairs on that one if we did the right Lewis structure. But which one of these will have, or what forces will a sample of these 2 molecules have? If I have a pure sample of each one of these 2, do they both have dispersion forces? The answer is yes. Are they both polar molecules? Well, hopefully you can see that, I mean, this has got some asymmetry going on and some really electronegative oxygen, so both of them do. Yeah, asymmetry and polar covalent bonds. So both of these molecules are going to be polar. So far, both of them have dispersion and dipole-dipole. But what about hydrogen bonding? Which one has hydrogen bonding? Do either of them? Well, only the bottom one has hydrogen bonding. Hydrogen bonding has to be this bond, the oxygen-hydrogen. That's what makes hydrogen bonding possible in this molecule. So I would expect, if I said which one of these has a higher boiling point, I would pick the one that has hydrogen bonding in it to have the higher boiling point. Okay, pause the video and answer this quiz, and we'll talk about it. So the weakest is dispersion, and the strongest is hydrogen bonding. All right, so here is an application of these things. Which of the compound has the lowest boiling point? Pause the video and see if you can figure out which one would have the lowest boiling point. Another way to ask yourself this question would be, which of these has only dispersion forces present? All right, pause the video and see if you can get which one has the lowest boiling point. Okay, the answer is that ethane on the bottom. In order for something to have the lowest boiling point, if we can identify something that only has dispersion forces present, then it's going to be the lowest boiling point. Ethane is a nonpolar molecule. It's not going to have dipole-dipole or hydrogen bonding. It's only going to have dispersion forces. All the other things have an OH or NH bond and are going to be polar and have hydrogen bonding. So they're going to be have much higher boiling points. Now, just looking at I could ask the question, which one would have the highest boiling point? Well, I would say water would have the highest boiling point of that list. And the reason I say that is because anytime you put some hydrogen and carbons, it makes it a little bit nonpolar, some aspects of nonpolarity, and so it's going to kind of offset that hydrogen bonding that's present a little bit, and it'll be easier to get it into the gas phase. So I would choose water as having the highest boiling point because I know the effect that these nonpolar bonds will have on the sample. Out of these two, which would you predict would have the highest boiling point? Number 3 or number 4? Well, I would probably say, both of these, this is methanol and this is ethanol. This has a higher molar mass. There's more dispersion forces. They're both polar molecules. They both have hydrogen bonding, but this one actually has a bigger dispersion force effect. So I'd actually say that this one would be a higher boiling point. You can actually Google the boiling point of ethanol and methanol and see if we're right. I don't know exactly what the boiling points are, but see if it's right by Googling that. This is an example in your textbook predicting the relative boiling points. I'll let you look at this, and the answer's right below. I won't spend time talking about it. Okay, so here's a molecule of CH3Cl. What kind of cohesive forces would be in a sample of this molecule? pause the video and then I will answer it. Okay, the dominant force would be dipole-dipole interaction because CH3Cl is a polar molecule. There would also be dispersion forces present or London forces. I'd accept those as synonymous. There is no hydrogen bonding in that molecule, but the dominant one is dipole-dipole forces. Answer this question and pause the video and then I'll answer it. In order for something to have a high vapor pressure, it means it has less cohesive force. So I'm looking for the thing that has the lowest cohesive force. So if I can find something in that list that only has dispersion forces, that would mean it would have the highest vapor pressure. So gosh, everything on that except for methane looks like it's going to be they're polar molecules, and some of them have hydrogen bonding. Methane is a nonpolar molecule, doesn't have dipole-dipole interaction or hydrogen bonding. So that methane would have the highest vapor pressure and the lowest boiling point. Just a little interesting note about how perfumes are designed. In an expensive perfume, they will have lots of different molecules that have different cohesive forces present in the liquid phase. And as you spray that perfume on, some of the molecules are going to evaporate quickly into the gas phase, and some of them will be not as quickly evaporated. And so if you have a really good perfume, it lasts a long time, but kind of the smell kind of changes over time. It doesn't smell the same in the first minute as it does after a few hours. And that's because there's different molecules escaping into the gas phase at different times. The molecules with the weakest cohesive forces are the ones you smell first, and the ones that have stronger cohesive forces would stay on your skin longer and then evaporate. A word that we use in chemistry is volatility. It doesn't mean that molecules get angry and attack other molecules, but the volatility means if something can go into the gas phase quite easily, it is what we call a volatile chemical. It doesn't have very many cohesive forces. And some molecules are characterized as semi-volatile. So we say liquids that vaporize easily have a high vapor pressure, we call them volatile, which means they have weaker cohesive forces. And this last statement, more endothermic, we really haven't talked about exothermic and endothermic things, but phase changes can be considered exothermic or endothermic. If something evaporates really quickly, it absorbs energy from the environment really quickly, and the liquid feels really cool. Energy is being sucked into that to do the phase change. That when energy goes into something to do a phase change, it's called endothermic phase change. So things that are very volatile are more endothermic. The other time we use endothermic or exothermic is like when heat is released in a chemical reaction like combustion. One of the products is heat or energy, and we call that reaction an exothermic reaction, and it has to do with the bond energy. This is different. This is just energy going in to make the phase change. So liquids that don't vaporize easily have a lower vapor pressure. We call them non-volatile. They have stronger cohesive forces and they're less endothermic. There is one part of this chapter that is a little bit of a calculation thing that we need to learn how to do. In order to do this, we need to define what a solution is. And if we go clear back to chapter 1, we learned that we can have homogeneous mixtures of things, and they're called solutions. And a solution then is going to have at least two components. It'll have a solvent, which is the thing that's present in the most amount, and it'll have a solute or more than one solute. And the solute is the thing that's not present as much. So if I have some Kool-Aid that I've mixed up and I'm drinking some Kool-Aid, what would be the solvent? Well, of course, water would be the solvent. That's the majority component. And the Kool-Aid would have lots of solutes. It might have some sugar, or have some coloring molecules, some other flavoring, so it's going to have lots of solutes. But that's, a solution is defined as a homogeneous mixture of two or more components. And now we're defining those components as solvent and solutes. So now we're going to learn about some of the concentration units for solutions. Here are some that are very common: percent by mass, percent by volume, part per million, and molarity. Percent by mass and percent by volume are used a lot in the medical industry. Like if you have an IV, it'll be like a 5% mass M/M, which is mass percent, or 5% volume mass percent. So and the different units are just the way that the use and also the way that the solutions are made. It's conducive to either be a mass percent or volume percent. Part per million is a concentration unit that is used for typically for pollutants in water and in air and in soil. Very low concentrations, and part per million means exactly that. If I had one carbon dioxide molecule in 1,000,000 air molecules, it would be 1 part per million carbon dioxide. A typical concentration of carbon dioxide is 380 or 390 part per million. So out of 1,000,000 air molecules, which are comprised of all of the things that aren't carbon dioxide, nitrogen, oxygen, everything, we have 380 or 390 carbon dioxide molecules. The one concentration unit that chemists use the most is called molarity. And that's the one that I want you to focus on and know how to do some calculations for the final exam. The definition of molarity is the moles, the number of moles of the solute divided by liters of the solution. So molarity is mole per liter. That's what molarity is. Let me go back and do this. What is the molarity of a 300 ml of a sodium chloride solution made using 10 grams of sodium chloride? Hopefully I brought a calculator. Okay, so all right, so molarity, here's the symbol for molarity. It's a capital M. And the units on molarity are moles of the solute, whatever that solute is, divided by liter of the solution. So that's the definition, mole per liter, moles of the solute per liter of solution. So the problem that was listed said, what is the molarity of a solution if I have 300 milliliters of solution, and that is made by putting in 10 grams of NaCl. So essentially, I'm making a solution. I'm dumping in 10 grams of NaCl, and then I'm going to add enough liquid to make a volume of 300 milliliters. Okay, so that's what the problem's saying. All right. Well, molarity. What molarity is? I need to figure out the moles of the solute. So can we figure out moles of the solute? Well, I sure hope we can. Mole, the solute is NaCl. So I have 10 grams of NaCl. And the molar mass, gosh, I don't even have a periodic table with me. I think it's 23 plus 35, 58.4, I don't know, 0.4 grams per mole. That's close enough. Okay, so I can divide by 58.4 gram per mole of NaCl. Gram cancels out. Now I know how many moles of NaCl. Well, remember for molarity, I'm getting moles of NaCl per liter. So I calculate that value, whatever that is. Let me see if I have a calculator. Okay, so the number of moles is 0.171 mole of NaCl. So the molarity of NaCl is going to be equal to 0.171 mole NaCl divided by the volume, and the volume has to be in liters, so I have it in 300 milliliters. I need to put that in units of liters, which I just move a decimal point over 3. So that is mole per liter, so I divide that by 0.3. So the molarity of this solution is 0.57 molar NaCl. And then the units on this M are mole per liter. We actually say molar, which sounds kind of retarded, but it is. That's the correct terminology. So that's how you do a molarity problem. And you do need to be able to do these calculations, know what molarity is and how to do simple molarity calculations. Okay, so here's a quiz for you to do. So pause the video, and then we'll show you how to do this. Okay, the correct answer is 1.67 molar. All you would do for this is take the mole of calcium chloride, 1.25 mole, divided by 0.750 liter, because this has to be in liters, and that's the molarity, mole per liter. The solute is calcium chloride, and the molarity is 1.67 molar. Another quiz, pause the video and see if you can get this answer. The right answer is the salt is the solute. Water would be the solvent. Okay, well, here's another sodium chloride question asking a little bit different. How many grams of sodium chloride are present in 2 liters of a 1.5 molar salt solution? Well, how in the world do we do this? Let me show you how. Okay, so let's write down everything that's in the problem. We have the volume is equal to 2.0 liters. The molarity is equal to 1.5. And I'm going to actually write mole NaCl per liter, because that I want to be able to do unit analysis on that. And my question is, how many grams are present? That's what I want to do. Okay. So molarity actually is a conversion factor between moles of a solute and volume of a solution. So we've been doing conversion factors for several months. That can mean 1.5 mole of NaCl is equal to 1 liter of solution. That's what that ratio means. The molarity is what that means. So if I have volume, if I start with volume, of 2.0 liter, and I choose somehow to make the liter cancel out using the molarity to cancel out liter. So 1 liter goes on the bottom and 1.5 moles of NaCl goes on top, then liter cancels out. And right now I have 2 times 1.5, or I have 3 moles of sodium chloride in that 2 liter of solution. The question asks how many grams. So can I do one more conversion factor where I know 1 mole of NaCl is equal to, what was that, 58.4 grams of NaCl. And if you do that, it'd be 3 times 158.4, which is, oh, I don't know, 100 and, I don't know where I put my calculator. 175. So with the right number sig figs, it'd be 180 grams of NaCl would be present in 2 liters of that concentration. So that's how you do molarity problems. Remember, molarity is equal to mole over liter. And the other way I could have solved this problem is I'm given volume and I'm given molarity, I can solve for mole. So mole is equal to the liter, the volume, times molarity, which is in units of mole per liter. And so we have volume times concentration, liter cancels out, and we're left with mole. So for this problem, I could have solved it like this. I could have said 1.5, oh no, sorry, 2 liters. 2 liters times 1.5 mole per liter. And that will give me moles, and then I just would go the last step. 1 mole is 58.4 grams. And there you go. So either way works. I like using the molarity as a conversion factor like we've been doing all semester, but this is also a good way to do it. And you do have to do the unit analysis as well. Okay, why don't you do this problem and pause the video while you work on it, and then we'll see how you did, and I'll work the problem. And the answer is 0.8 molar. Again, using the definition of molarity allows you to solve these kinds of problems very easily. So let me show you how to work this problem. I think that's 23.2. Okay, so to solve this problem, I want to know what the molarity is if I have 23.2 grams of sodium chloride and I put that in 500 milliliters of solution. Okay, so to do this, I need to just follow what molarity means. I have 23.2 grams. 23.2 grams. I divide by the molar mass. So grams cancels out. Then I'm just going to divide by the solution volume in units of liter. And there you go. The units are mole per liter. And plug that in your calculator. You should get what we said the answer was. 23.2 divided by 58.4 divided by 0.5, and that is indeed equal to 0.80 molar NaCl. So there you go, piece of cake. Okay, that's pretty much all the calculations that you need to do in chapter 12. Molarity calculations. The next part of this chapter is just we're going to talk about water and some water pollution issues. So here's a quiz. Why don't you pause the video and answer this quiz? So the only thing that's incorrect on these statements is water is not a good solvent. That is wrong. Water is a really, really good solvent. In fact, water is called a universal solvent because so many things are soluble in it. Ionic compounds are soluble in water. A lot of them, some of them aren't, but many are. Polar organic molecules are soluble in water. So water is a really good solvent. 1, 2, and 3 are absolutely correct. Water has a high boiling point because of the hydrogen bonding. Water expands when it freezes, also because of hydrogen bonding. And number 3, water is the most abundant liquid on the planet. Also true. Without water, we would not be able to exist. In fact, when they send exploratory scientific things to Mars, one of the main things they're looking for is evidence that water was there, or maybe water is there. Because if water is present, then there's a chance that life perhaps perchance evolved. So here's the thing about boiling. I said. So just a little review about boiling, because boiling is kind of an interesting phenomenon, and if you try to explain it to someone, it's kind of difficult to explain unless you really understand what's going on. So when the vapor pressure of the gas coming off the liquid is equal to the atmospheric pressure, then you're at the boiling point. And gas bubbles form within the liquid. It's not just a surface phenomenon like evaporation. And the boiling point can change depending on the atmospheric pressure. Like I said, in Mount Everest or the Himalayas, the boiling point is going to be lower than somewhere in lower elevation because the atmospheric pressure is not as much. So Mount Everest to be lower, Death Valley would the boiling point be higher or lower than normal in Death Valley? Well, Death Valley is actually below sea level, so the pressure is going to be greater in Death Valley, so the boiling point will be slightly higher for water in Death Valley. Pressure cookers also a higher boiling point because of the way the steam is trapped and increases the boiling point. Here's a really beautiful picture of all the possible phases of water. We have liquid and solid, and we can't see the gas phase water, but it's there. Water makes our planet what it is, and it's such a valuable, important resource. Wherever there's water, there is life. And that's one of the criteria that scientists look for when they're exploring places, is if there's water, there can be maybe life there. So here are some unique structures and properties of water. It's highly polar. It's a small molecule, really large dipole between the hydrogen and oxygens. Also has hydrogen bonding, which is a really important force. Hydrogen bonds are almost as strong as covalent bonds. Now, hydrogen bond is just an attraction between molecules. You're not sharing anything like you are in covalent bonds, but it's such a strong attraction that it's actually called a hydrogen bond. This hydrogen bonding makes water expand when it freezes, which means the ice is less dense than liquid water, which is a huge property. If that didn't happen, all the fresh water would be trapped in the bottoms of lakes and oceans and be in an unusable place. So this property of water is hugely important. The ice will insulate the marine life in the water below, So the air temperature can get well below freezing, and the ice can get colder, but the water below the ice is insulated, and so it protects the marine life that's in the water. I'm sure these are pictures of students' brains near finals. Yeah, the one on the left is a brain that in the beginning of a semester, and at the end of a semester it's turned into the thing on the right. But seriously, that was supposed to be a joke, you know. It's kind of hard to be funny when there's nobody here. But anyway, that's an example of what happens to cells when water expands and ruptures the cells. The head of lettuce on the right was damaged by freezing, and it just destroys the cellular structure because the water expands. That's what happens in frostbite. It actually will freeze cells in people's extremities, and the cells die. And a lot of times frostbite can be severe enough that you'll have to have toes amputated or feet amputated or fingers or your nose or ears. I mean, anything when there's not really great blood supply is prone to having frostbite that actually destroys the cells and kills them. We talked about water being the universal solvent. It dissolves many organic and inorganic substances and ionic compounds. Water is the bomb. We just are so lucky to live in a planet that is a water planet, live on a planet that's a water planet. Our chemical makeup, we're about 70% water. We really are just big bags of water walking around with, got some other trace minerals and metals and some other things, but mostly we're water. So where is water and how did it get here? Well, there's some people think that the water on our planet came very early in our planet's beginning stages when there are tons of asteroids and floating around and impacting the Earth. That's one proposal of how so much water got on Earth. The water that is here, we live in what we call a closed system. Everything pretty much that's in the Earth, on the Earth, in the atmosphere, stays in the Earth, on the Earth, or in the atmosphere. It doesn't really escape into space. We have a closed system. And we don't really have asteroids hitting the planet, adding things. Once in a while you have a rogue meteor or asteroid that might come close. But, for the most part, we're pretty static as far as the things are being added and taken away from the Earth system. There's only a small fraction of water that's usable in lakes and streams. Water is by far the most abundant thing. You have all the oceans and everything, but only a small, tiny fraction is in a usable form in lakes or rivers or aquifers, somewhere where people can use it. Groundwater, 2.6%. Oceans, which isn't really usable because it's salt water, but that gives you an indication where the water is for the most part. Water, the hydrological cycle is a really important Earth system. The water evaporates from the oceans, gets into clouds, the clouds move over and rain on the land, and we have this big cycle of water moving. And as the temperature of the globe changes, those hydrological cycles are going to change as well, and we're going to get different weather patterns and different precipitation patterns, and some places that are deserts might become really wet, and some places that are really wet might become deserts. We're not exactly sure what's going to happen, but there's lots of predictions. Here's a picture of the hydrological cycle. The geologists really study a lot about water movement underground, or hydrology is the science of people that study what water does and how it moves. There is a lot of groundwater movement. It's usually very slow, but it can percolate down into the ground and then get be tapped by wells or get into oceans and rivers and stuff. The surface runoff is very rapid. And there's a lot of evaporation and transpiration from the plants anyway, it's a big old cycle. Condensation, precipitation, movement, but only a slight percentage is actually in a usable form. So the next few minutes we're just going to talk about some of the water issues. We are just so lucky to live in a place where we can pretty much go anywhere in the country and be confident that our water is not going to make us sick. Most of the world's population lives in a place where they do not have clean water, that drinking the water will make you sick and can maybe and probably will kill you, whether it's human pollution or chemical pollution or natural things in the water. We're just really lucky, and I hope you remember that. There really isn't any reason why you need to drink bottled water in the United States. It's an unnecessary expense, because the tap water, although you might not like the flavor, it's fine for you. It's healthy. It doesn't have any bacterial or viruses or things that are going to make you sick. So bottled water is a luxury, and all those plastic bottles that people throw away is a really bad environmental problem. So if you're going to drink water, try and do tap water, or reverse osmosis, purify your water at home with a reverse osmosis system or something. We'll talk about that in a minute. But there's many different solutes in water. The tap water isn't pure. There's calcium and magnesium and carbonate and all sorts of different solutes. And we like having things in our water. It gives water its flavor. Distilled water, if you ever had a drink of distilled water, is actually doesn't taste right because there is no taste. So we like having some of these solutes in the water. Some of the things that are in the water are harmful, some are beneficial, some it just doesn't matter. But like I said, the tap water, everything is either doesn't matter or it's beneficial. We really don't have harmful things in the tap water here in Utah County anyway. As water goes through the ground, it picks up a lot of solutes. A lot of these ionic compounds can be dissolved in the water. What makes hard water are the calcium ions and the magnesium ions. These things, if they're present in water to a large extent, they can precipitate out, and you get hard water stains. You can get precipitation in pipes and stuff like that. They're okay for you. They're not bad for you. In fact, calcium, we like having calcium and magnesium in our diet. So hard water is okay. It's just soap doesn't work as well in hard water, but we like to drink it, and it's not harmful for you. Some of the bad things that can be found in water are, most of them are bacterial. The bad things are cholera and typhoid and dysentery. And 80%, this is a staggering number, 80% of illnesses come from polluted water worldwide. Not in the United States. This is not an issue here, but worldwide in developing nations, 80% of the illnesses are waterborne. Again, I want to reiterate how lucky we are to live in a place where we pretty much are guaranteed to have safe drinking water. You can have chemical contaminants as well. Arsenic is something that is a big concern in third world countries, because they tap into wells that might have high arsenic concentrations, and arsenic is a semi-metal, and it can actually cause some serious illnesses and death if the arsenic concentrations are high enough. So that's something that is measured, and people try to remediate if there's arsenic in a well, and it's a naturally occurring thing in many parts of the world. So that's kind of an issue. You can't just tap a well and think it's going to be 100% safe. You got to test it and make sure that it doesn't have anything in it. Sometimes there'll be other contaminants from pollution spills, from oil spills, or from other things that seep into the groundwater that you have to be aware of. One of the big things that's happening in the oil industry is a process called fracking, or hydrological fracturing is what it stands for. And essentially they pump down some proprietary mixture of these solvents that kind of dissolve oil that might be in oil shale, and they crack the ground as they pressurize, force this stuff into it, and it makes the oil come out. But the problem is there's been evidence that some of this fracturing chemical has been seeping into groundwater and polluting groundwater in places in the U.S. where fracturing is done, or fracking is done. Anyway, there's some documentaries you can listen or watch called Gasland. I think they're Gasland, about people lighting their faucets on fire because there's so many organic solvents from the fracking. So anyway, there are issues, and there can be pollution in the water that you drink, but for the most part, city water is treated and it's normally safe. But there are some exceptions to that you should be aware of. So as I mentioned, the biggest problem for water quality are biological in nature. 80% of worldwide illnesses are waterborne, and mostly from biological contaminants, mostly from people and animals having feces go into the water and then people drinking that water. I think these are pictures of Giardia lamblia. It's one of the critters. It's not a virus. It's not a I can't remember it might be a type of bacteria. I'm not sure. Maybe not. But anyway, Giardia is a biological contaminant. And if you drink water, if you're out hiking in the backcountry and you just drink water from a stream, there is a chance that you can contract Giardia lamblia, and this stuff will make you really sick. It usually doesn't kill you, but it just gives you diarrhea for weeks and weeks on end. And it's caused by animals and people having feces close to the water or in the water that you're drinking. So that's why whenever you're in the backcountry, you need to treat your water to get rid of any biological contaminants that might be there. Oh, here's a picture of Giardia, and E. coli can make you sick. Different strains of E. coli, and it's really an indication of water pollution. And so, water treatment plants will actually test for E. coli, and if the levels are high, they'll know they've got a contamination problem. They need to treat the water better. So this is a test that is done a lot for water quality control. There can be chemical contaminants. People can pollute the water by dumping waste into streams, rivers, and lakes. You should never, here's Mama Caka telling you some more things you shouldn't do. You should never, ever, ever dump any chemical, motor oil, or anything in a storm drain. Storm drains, the water that goes into a storm drain is not treated. It goes right into the lake. Here in Utah County, it goes right into Utah Lake. So you don't want to dump anything down a storm drain. You need to dispose of chemicals in a proper way. Take them to a transfer station or a waste recycling thing, and take care of any oil or organic solvents that you have, or gasoline. Don't pour them down the storm drains. Sometimes, the things that are air pollutants, they'll get rained out, and the rain washes them out of the air, and they get into the water. So you can actually have, even though they're gas phase, through emissions, they get into the water supply. Another big issue for water quality is just using pesticides and fertilizers. There's actually a really big problem, people using too much fertilizer on these big farms, and the nitrates get washed into the rivers, and the excess nitrogen causes the water quality to really go down. There's algae blooms, and the water quality goes down because the oxygen content of the water goes down. Fish die, and all sorts of things happen. Phosphates are another big problem. So a lot of times farmers don't realize that too much fertilizer is bad. They need to calculate how much they need so it doesn't get into the drinking water or into the rivers that impair the water quality in the rivers and lakes. Some of the other things that can get into water are organic contaminants. Remember, volatile, they go in the gas phase easily, but they can get into the water. Benzene, carbon tetrachloride, and other, or non-volatile. You don't need to know these specific things, but I would like to know what the main water pollutant is, and just some of the issues for water quality that I've talked about. I wouldn't ask you these specific things about names of organic contaminants. That's where they come from: gasoline, pesticides, paints, and solvents. Organic contaminants can be really, really bad for you. They can increase your cancer risk, liver, kidney damage, central nervous system damage. So, we don't want to be exposed to these organic solvents. But like I said, culinary water is usually really, really safe, and it's tested, and they have to report if there's anything in the water of concern, and they have to take care of it. Some of the inorganic contaminants, nitrates. If you get too much nitrates in the water, from example fertilizer, you can actually have this hemoglobin's ability to diminish. Your body can't carry oxygen as well. So that's a very rare thing. It doesn't really happen anymore, but it has happened. I even forget the name of the stuff. Metals, mercury and lead, these are bad to be in water. And boy, if you've got mercury in your water, that's a real problem. Usually what happens with the mercury type of thing is that it becomes what's called methylated. It gets a hydrogen and a carbon and hydrogens on it, and then it can get into soils and into plants, and then the fish can eat it. And this mercury, because it's methylated, it's got this hydrocarbon, it can actually get concentrated into fish. Fish that are in the higher food chain, like tuna, is an example of a fish that's pretty high on the food chain in the ocean. Tuna eats a lot of smaller things. They eat smaller things, and tuna can actually concentrate the mercury, and it's actually fat soluble, so the mercury gets concentrated in the fat of these fish. And anyway, it can be very dangerous to eat these higher level fish, especially if you're pregnant or if you're a developing kid or whatever. You don't want to eat more than a can of tuna a week, because you don't want to take the risk of increasing your mercury intake, because any mercury is bad, and when it's methylated, it's in the form that can actually cross the blood-brain barrier and cause all sorts of problems for people that have high levels of, or ingesting high levels of mercury. And lead's the same kind of thing. It's a little bit different. It doesn't become methylated like mercury, but it can be, in the water as a lead ion, or it can be, it's more as in the ionic form that people would drink. And it actually makes you go crazy and impairs your neurological ability if you have water that has lead in it. That's really, really bad. There's some people that think that the fall of the Roman Empire was caused by the emperors becoming crazy, because they would drink lots of wine that were stored in lead-lined containers, and so they had essentially lead poisoning, and it made them go nuts. There can be some radioactive contaminants. Not really a big issue, but if you have an area that has a lot of uranium mining or deposits, then there can actually be radioactive material in the water. Down by Moab, there was lots of uranium, and there used to be very active uranium mining going on. And when you mine something, you get all your waste rock out, and you get the uranium that you want. You have all this waste. They're called mine tailings. And they were actually just dumped by the Colorado River down by Moab. And it was found out that because these mine tailings still had, traces of radioactive material, that was seeping into the Colorado River. And about 3 or 4 years ago, it was deemed to be a Superfund site by the EPA. And they have gone in and they've started, and I don't know how far they are into completion. They're essentially hauling out all these mine tailings that took decades to build up by the Colorado River, and they're taking them to a very secure landfill that's lined that won't get into groundwater. So they're removing all that radioactive material because they didn't want the radioactive material to be leaching into the Colorado River anymore. So that's something that is an issue in some places, and here in Utah that's an issue. So if you drink water or ingest things that are radioactive, that increases your cancer risk. Just a few more minutes and we'll be done with this. A little bit about home water treatment. Is hard water good for you or bad for you? If you remember, I said it really isn't bad for you. Hard water is defined as water that has pretty high calcium and magnesium ions in it. You can actually get water softening things for your home. And essentially what they do is they have a salt exchange membrane in here that exchanges those calcium and magnesium ions for sodium ions. This is a picture of the ion exchange material that this might happen in a water softener. It's called zeolite. Anyway, the sodium ions exchange with magnesium and calcium, and then essentially the zeolite it wants to keep the magnesium and calcium in these holes. They're the right size. But water likes to keep the same charge. It's got to have the same number of cations as it did before. So salt water's sodium ion is put in there, and the calcium ion is trapped, and the magnesium ion is trapped in the zeolite. And then you can regenerate this. They'll flush this out as part of the water softening treatment. You flush it with concentrated sodium chloride, and it can be used over and over and over and over. So it's a great thing to get rid of calcium, magnesium. The dangers is, some people don't think you should be drinking soft water because the concentration of sodium ion is greater than with normal water. And that's true, but there have been studies showing that drinking soft water is not really that bad for you. There aren't, it doesn't taste salty, and it's not a huge amount of sodium ions that are put in. But if you have high blood pressure or need to watch your sodium intake, you definitely shouldn't drink salt water. But soft water, you should never drink salt water because that can kill you. But soft water, it really shouldn't hurt you unless you have high blood pressure or have to limit your sodium intake. I personally, at my house, I have a soft water system, and then I have a reverse osmosis system that gets rid of all the sodium. So I like having soft water because it actually makes the detergent work a lot better. Soap works better. It feels really great when you're taking baths and showers with soft water. It's really nice water. And then I use a reverse osmosis system for my drinking water and cooking water. One thing that you can do are these Brita filters, and essentially what a Brita filter is a carbon activated charcoal or carbon, and it really effectively removes any organic solvent that might be there. Or if you have chlorinated water, the chlorine would actually be removed by the activated charcoal. So, if you don't like the taste of chlorine in tap water, really all you need to do is get a Brita filter and use that, and then the chlorine taste would be gone. And they last for many, many gallons, and then you just get a new Brita filter and you're good to go. That's if you don't like the chlorine taste. So just the last thing that we're going to talk about in this chapter is reverse osmosis. I mentioned that at my house I have a reverse osmosis. What osmosis is a natural phenomenon where if you have a semi-permeable membrane, or a membrane that will let some things pass and not other things pass, a really good example of a semi-permeable membrane is a cell. Cell walls are semi-permeable membranes. Some things can get in, some things cannot get in or out, right? It works both ways. Well, osmosis is a natural phenomenon that if you have a membrane, nature wants the concentration of the solute to be the same on both sides of the membrane. That's a natural condition. And so if you have something that is a higher concentration of, say, salt on one side of the membrane, water molecules will try to get through that membrane to make the concentrations equal. Okay, that's a natural thing. Reverse osmosis is not natural. We have to make it be reverse osmosis. So this is a picture of normal osmosis, where you have salt water here and the water is trying to go through to make the salt less diluted. And here's a semi-permeable membrane. Well, for reverse osmosis, we actually want pure water. We want to get rid of all the things that we don't want, like salt or organic molecules or whatever, things that we don't want in our water. We want pretty pure water. And so reverse osmosis, you actually have to make it happen. It's not natural. You actually have to apply pressure to this side that has the things in it that you don't want and make the pure water flow through that membrane. This is a really good way to get pretty much pure water and leave all of the things you don't want on this side, and this will come out your tap. I like reverse osmosis. It's kind of expensive, but it's really good water. You can purify tap water, like I said, with this. You can actually use these on big scales to desalinate ocean water. It actually costs quite a bit to desalinate ocean water, but you can make pure water by reverse osmosis. A very expensive proposition, though. So that is the end of chapter 12. Hopefully everybody understands what I'm saying, and it's clear. Just work problems, do the sapling homework. I may be back in class for this chapter. I may not, but I will keep you guys posted via Canvas. And anyway, thank you, and we will talk to you later.